Suppose you try to move a crate by pulling upward on the rope at an angle of 30 degrees above the horizontal. How hard do you have to pull to keep the crate moving with constant velocity? Is this easier or harder than pulling horizontally? The weight of the crate is 500 newtons, and the coefficient of kinetic friction is 0.40, and we know that theta equals 30 degrees. So what is it asking us to find is to find the tension in the rope. It's like that's how hard you have to pull on the rope, so the tension of the rope equals the applied force that you have. To do this, let's identify all the forces that are acting on the crate. So I'm going to go ahead and start drawing my free body diagram, which I start with drawing x, the coordinate system. I'm going to call positive x going to the right and positive y going to upwards. And here's putting the particle, the crate making, modeling as a particle and putting at the origin. Now let's go to our picture and see what are the forces acting on it. So there is this tension on the rope at a certain angle. So the weight of the crate downwards, and then we have the normal force that is going upwards, and then we have the friction, kinetic friction, because it's moving. Although the system is in equilibrium, velocity is constant and acceleration equals 0 by x, and acceleration by y also equals 0. We have to keep that in mind. So if we translate these forces into our free body diagram, we have the weight going downwards, normal force upwards, and then we have a tension at 30 degrees, and the friction, kinetic friction, opposite to the motion. So let's call this angle to be theta, and then immediately let's resolve the tension into components. It would be easier for us to write our Newton's second law. So we have the x component of the tension, Tx, and then we have the y component of the tension, Ty. So we don't need this anymore, and let's write Tx equals T cosine theta, Ty equals T sine theta. Now let's write Newton's second law. In this case, because the system is in equilibrium, which means it has no acceleration, sum of the forces should equal to 0. This translates into sum of the forces by x equals 0. Sorry for the phone call. And let's put the vector sign in here. And I'm sorry. And then we'll write sum of the forces by y. No vector. We are in component forms, equals 0. So now let's put all the forces. On the x-axis we have Tx minus Fk equals 0. And then on the y-axis we have a Ty plus normal force minus weight equals 0. Now let's recall Fk is mu k times normal force. And then substituting the Tx and Ty into these equations, we will get, Tx as a T cosine theta minus the value, the expression for mu fk, so that's a mu k times normal, equals 0. And then for the second equation, we're gonna plug in the ty as a t sine theta minus plus normal force minus weight equals 0. So what we have two equations that happen simultaneously, but two unknowns. We can solve the equations. We can find the normal force from one equation and plug it into the second equation. So let's find it from the first equation. The normal force will be equal to t cosine theta over mu k, and plug it into the second equation right here. We'll end up getting t sine theta plus t cosine theta over mu k minus weight equals 0. I think in this situation we can solve for t. So t, I can write sine theta plus cosine theta over mu k equals the weight. So at this point we can even plug in the numbers. So tension equals weight divided by the parenthesis sine theta plus cosine theta over mu k, and the weight was given to us, and that was 500 newtons, divided by theta was 30 degrees and mu k was 0.40. Okay, so we have sine 30 plus cosine 30 divided by 0.40 equals about 188 newtons for tension. Now let's plug this in back into our equation for the normal force and get normal as well. That equals 188 newtons times cosine 30 degrees divided by 0.40, and we get 406 newtons. Well, as you can see, normal force is less than the weight, which was 500 newtons. And the tension required is little less than the force that we needed in a different problem, similar problem earlier when we pulled the crate horizontally. You can check my friction example 1 and see that we required 200 newtons force to move the crate, but at an angle of 30 degrees, the tension is a little bit less. So, which tells us the crate pulled at the angle of 30 degrees is easier to pull than if you pull it horizontally. Now you can expand this problem to try to practice asking a question: how hard do you have to pull on the crate initially to get it moving, so to break it loose? If you pull upward on a rope at an angle of 30 degrees above the horizontal. Thanks for watching. Stay tuned for more to come.